Now, as mentioned already by Georg, we will now come to the specialization topics. And the first specialization is in applied synthesis chemistry. And the speaker on this topic will be Professor Michael Schnürch. He's head of the Institute of Applied Synthesis Chemistry, and he's a professor in metal organic chemistry as well. And he will now tell us about this specialization.
Thank you, Peter.
Yeah, you didn't need the microphone because we are recording it. Yeah. No.
After you've seen the general structure of the master programs in chemistry, I want to start now with showing you the first specialization, which is the specialization on synthetic chemistry and specifically on applied synthetic chemistry. What training will you receive here? Of course, most importantly, a comprehensive training in preparative synthetic chemistry in various aspects, theoretical and most importantly, practical knowledge of important synthetic methods in such fields as bioorganic chemistry, inorganic chemistry, and macromolecular chemistry. Of course, if we make something, we also need to characterize to make sure that we also made what we wanted to make. And then, of course, we're going to look also at the technological utilization potential. The basic module consists in this master program of 2 lectures, industrial chemistry and theoretical chemistry. In the specialization area, there is 1 big lab course, the advanced laboratory course in synthetic chemistry. Then you can select between specialization areas, or let's say these are the specialization areas within the applied synthetic chemistry module. Molecular basics, inorganic molecular chemistry, physical organic chemistry, and organic chemistry 3. Then synthesis of materials, very important topic as well, inorganic or organic materials. Analysis of course, synthesized compounds or materials, as I've already said, very important, either on the molecular or on the material level. And then technological aspects of synthesis like industrial synthesis, so scale-up, kinetics, and catalysis. Then you can choose between elective modules such as advanced spectroscopy, so still in the field of analysis, NMR of course, or all sorts of vibrational spectroscopies. And then advanced inorganic chemistry, where we have organometallic chemistry, coordination chemistry, or theoretical molecular chemistry, and advanced polymer chemistry, where we have specific specialized synthesis methods for polymers or polymer characterization, also a topic on its own. And then advanced organic chemistry, consisting of catalysis in organic synthesis, organic chemistry 4, where I want to mention that it's not necessary to do organic chemistry 3 before organic chemistry 4. They're independent from each other. And additionally, nomenclature in organic chemistry, which is a quite complicated topic eventually. Then chemical biology 1 and 2, and in medical chemistry, we have medicinal chemistry 1 and 2. Then another option are biomolecules, the synthesis of biomolecules or the synthesis of complex natural products, and biomicrofluidics, lab-on-a-chip technology in the life sciences, where you have the basics of lab-on-a-chip technologies, live cell micro and organ-on-a-chip technologies, and rapid prototyping and polymeric microfabrication. We'll see in the examples of what's going on in our institute, maybe a little bit more that you can make more out of these names here. So if you go through the applied synthetic chemistry master, what are your employment options? Actually, in the end, you all want to have jobs, right? So a big one, of course, is the pharmaceutical industry. either developing active pharmaceutical ingredients in theranostics, which is a combination of therapy and diagnostics. Also here we have work ongoing at the Institute. Pharmaceutical production, of course, if you make a drug on large scale, you have quite some regulations, which is a specific topic on its own. If you are developing something, you might also want to protect it, so patent it. So you can either work on the one side to make the patent or at the other side where you approve eventually a patent. And quality assurance and management important in many different fields. Petrochemistry, still very important, large-scale organic chemistry or large-scale inorganic chemistry, where we make basically the bulk chemicals you all have used already, maybe in the synthesis lab course. Agrochemicals, plant protecting agents and stuff like that, also a big topic here in production of materials. Then polymers, the plastics industry, so-called, is quantity-wise one of the largest chemical sectors, where eventually you develop new monomers and polymers. For example, biodegradable polymers are a hot topic now. Polymer modification and additives to tune the properties. Man-made fibers, all the fabric you eventually wear contains not only natural but also some artificial fibers and smart materials. And renewable raw materials, of course, a big topic to get rid of oil-based eventually economy, where you use stuff like paper pulp or fibers of starch, material waste utilization, that a byproduct from some industry, eventually from the food industry, you make some valuable upgraded chemical out of it. Biogenic raw materials, or the chemistry biology interface where you could find employment. There are many, many companies also in Austria working in this field. Now coming for a moment to our institute. So how is the structure of the Institute of Applied Synthetic Chemistry? As all institutes, we have a head of institute, which would be myself actually, Michael Schnürch, and then we have the 3 research divisions: inorganic chemistry led by Peter Weinberger, macromolecular chemistry led by Robert Lisker, and the research division organic and biological chemistry is again headed by myself. Within these 3 research divisions, we have in total 9 research groups. So color-coded in blue are the ones in the inorganic chemistry research division, where we have the research group of Professor Kirchner working on metal organic chemistry and catalysis. We have the group of Peter Weinberger working on molecular magnets and thermochemical energy storage materials. And we have the research group of Professor Steinhauser working in applied radiochemistry. He's dual affiliated actually also at the Atomic Institute in Prater. Then the research division macromolecular chemistry consists of 1 research group of Professor Lisker, polymer chemistry and technology. And within the research division organic and biological chemistry, we have the research group of Martin Frauenlob, lab on a chip technologies, the research group of Hannes Mikkola, molecular chemistry and chemical biology, the research group of Professor Gärtner, stereoselective and sustainable synthesis, the research group led by Florian Rudolph, bioorganic synthetic chemistry, where I'm also a part of, and the research group of Professor Schröder, sustainable organic synthesis and catalysis. So now a few of the research topics we're actually dealing with at our institute. Here, thermochemical energy storage materials. Energy is a big issue, of course. We do not have a problem actually with having not enough energy. The sun alone would provide us with enough energy to cover all our demand, but of course it's not always available at the time when we need it. So we need to store energy as well. And for example, in the group of Professor Weinberger, they are working on such metal salt hydrates to store excess heat from a process via a chemical process and then release it when needed. In the research group of Professor Steinhauser, applied radiochemistry, they try to understand the origin and fate of radionuclides in the environment. So, of course, if there is an incident like a radioactive cloud tracked over Europe and it's kind of mysterious, where is it coming from? That's where this research group eventually comes into play to identify how and where this eventually contamination, if I may call it so, of a radionuclide or radioactive isotope came about. Then if we are in the research group of Professor Liska, you all, I guess, have been at the dentist at some point, and you eventually also got a filling already of one tooth, where eventually you got a little hole in there. And for example, in the group of Professor Liska for quite some time, they are developing polymers which can actually be used as dental fillings, and there's actually a high probability that some of you do have a filling in your teeth that actually originated here at our institute. Not only the polymer is important, again, you know that or have experienced that eventually they shine a light in your mouth after they have put the filling in there, which is then a specific photoinitiator, which then triggers polymerization, and then the polymer hardens actually in your tooth, and you get your stable and hopefully long-lasting filling in your tooth. Also 3D printing, for example, is here something which you can do with specific polymers and light-induced polymerization, as you see here. So very interesting, very forefront research topics covered in this research group. Then coming to the third research division, where we have, for example, the group of Martin Frauenlob, where they try to develop this human on a chip technology. So for the moment, if you do, let's say, testing of an active pharmaceutical ingredient, you would typically go to a simple cell culture, and there you have specific cells, and you look what your compound, for example, does to these cells. Of course, this is then just a very, very tiny portion of a real human, and in between you typically would need to go then also to animal testing or something like that. And it is tried actually to avoid or shift animal testing to a much later phase when you eventually on a very tiny chip, and you see here a €1 coin to show you the size of such a chip. We have in specific areas little tissue piles, I want to say, of various organs, for example, and you could kind of test your active pharmaceutical ingredient, to take this example, almost already on a full human scale, at least on a series of tissues stemming from the most important organs, and you can check, is it toxic, is it not toxic, or does it what it should do here. Then coming to the group of Professor Mikkola, generally working on the topic of molecular tools derived from synthetic chemistry and computational modeling. And these tools should then do different things. For example, you want to get compounds which help you to understand and manipulate biological systems. So first, of course, comes the understanding, and then when you understand what's going on, you can work on manipulating. Of course, that all goes into the direction of medical applications. Same with diagnostic and therapeutic strategies and devices. So this is the area of theranostics, and all these areas are actually interconnected to each other. Eventually, drug targeting and delivering, that you really get your active pharmaceutical ingredient to the location where it is needed, and not just spread it all over your body by eventually having it in your blood or by swallowing it, where you get a very unspecific distribution over your compound. Or, for example, in this group is also molecules and structures of life, like artificial membranes, for example, or like peptides, which are synthesized and then studied in this research group. In the research group of Professor Gärtner, one very interesting topic is the synthesis of metabolites for doping analysis. So you all know, as being Austrians, we unfortunately have quite a history of dopers in our country. That you either collect urine or blood from an athlete, and then you want to detect, or that's what most people think, you detect the compound which was used for doping. However, these compounds are very often quite rapidly metabolited to other compounds. So what you're actually searching for are stable metabolites, stable meaning not only detectable for a couple of hours, but ideally for weeks. And if you know from which doping agent, which stable metabolite is coming from, in the end, in your tests, you're not looking for the actual compound anymore. You look for the specific metabolite. And often they only have a mass spec for that and a little idea what could be the stable metabolite. And then comes the group of Professor Gärtner into play, tries to synthesize the suspected metabolite to elucidate the structure and also have material in hand then for validation of such a new doping test. Then in a group of Professor Schröder, one topic actually is the utilization of carbon dioxide. We all hear a lot of bad carbon dioxide actually. It's a greenhouse gas and causes a lot of problems with global warming. But it's actually also a raw material which you could use for doing quite some chemistry and making actually important compounds such as fine chemicals or fuels. So kind of closing the circle, you burn a fuel, you get CO2, and if you can make a fuel again of it, you would have a circular economy which would not increase your CO2 concentration in the air. And now coming to the final research group to show you today of Professor Florian Rudolph, where there are several PIs working, one being myself. And there are various topics, just like solvent-free reactions to increase sustainability, to decrease actually waste which you produce in a chemical process, because typically the solvent is the largest part in there. Also synthesizing active pharmaceutical ingredients, eventually stemming from a natural product. Here we see Edelweiss. Of course, Edelweiss wouldn't be the source. You cannot isolate such a compound in large quantities from a protected natural plant. So we need to find synthetic roots and then eventually make derivatives to treat diseases like coronary artery disease, for example. Then catalysis, and specifically biocatalysis, also a topic in this group. Where, of course, an enzyme is per se a quite environmentally benign and selective catalyst. That's what actually nature has designed these enzymes for, that they are very selective for specific transformations. and constantly a million of these processes are going on in your body. But here we are trying to exploit that for synthetic chemistry as well, and make specific compounds like this aroma compound vanillin, you for sure all know. Or wastewater treatment. In a wastewater plant, for example, you typically have first kind of dirty wastewater where you then add an flocculating agent that you can then sediment off actually most of the dirt and get clean water out. But these flocculation agents are not the most benign which are currently used. So in our group, we are also looking for biological, more environmentally benign flocculating agents. So thank you very much for your attention, and I hope you enjoyed this little overview of the Applied Synthetic Chemistry Master and the research activities at our institute.
Thank you very much, Michael, for this informative presentation.